Hello everyone, my name is Yutong from Georgia Tech. Thank you for joining my presentation, and I would like to share our result that shows microbubble properties and ultrasound frequency can modulate the blood-brain barrier phenotype. Microbubble enhanced focused ultrasound provide a physical method to transiently open the blood-brain barrier and improve drug delivery in the brain. As a key component of this technology, microbubble can interact with the ultrasound field and act as a mechanical oscillator. It is hypothesized that the observed changes in the blood-brain barrier permeability is related to the forces generated by the microbubble oscillation, including the direct oscillatory force, radiation force, and indirect shear forces. However, there is a limited consensus on how microbubble property and ultrasound frequency can contribute to their interaction with the vessel wall. Therefore, to bridge this knowledge gap, firstly, we build a mathematical model of microbubble dynamics and also its interaction with the surrounding fluid inside the elastic and porous vessel. Using this model, we study the impact of a range of system parameters on the microbubble dynamics. The mathematical model is tested using an in vivo experiment with monodispersed microbubbles. First, we would like to study the effect of microbubble shell property on the blood-brain barrier permeability. To do this, we modeled two clinical-grade microbubble with different properties. The affinity bubble has a lipid shell which is more elastic compared to the albumin shell of optism microbubble. Our mathematical model suggests that microbubble with a more elastic shell will have stronger oscillation inside the vessel. And then we performed in vivo experiment using the affinity and optism microbubble with the same size and inject same number of microbubble while keeping all other ultrasound parameter constant. Our experimental data suggests that the affinity bubble have a stronger acoustic emission compared to optism bubble, which is also agreed with our mathematical prediction. And then to see if these changes in the microbubble oscillation will have any impact on the blood-brain barrier permeability, we measure the vessel permeability using DCE MRI ultrasonication. K-trans value were significantly higher for the affinity microbubble group as compared to the optism microbubble group. We also measured the tech junction protein, which is considered to be one of the major components of the vascular barrier, and we found that there's a significant downregulation of this tech junction protein for the affinity group as compared to optism group. Together, this data indicates that microbubble with a more elastic shell are more potent in opening the blood-brain barrier. Similarly, we also found that larger 2-micron affinity bubble leads to higher K-trans value and stronger acoustic emission as compared to smaller 1-micron affinity bubble for the same acoustic setting. This data support the past observation by Dr. Konofago's lab. Finally, we want to study the effect of ultrasound frequency on the blood-brain barrier phenotype. To study the different forces involved, we also calculate the shear force on the vessel wall exerted by the microbubble oscillation. Firstly, we found that due to the resonance effect, the microbubble oscillation are similar when it's excited at 0.5 MHz and 1.5 MHz. But interestingly, because the microbubble oscillate at a faster rate at higher frequency, the affinity bubble exerts 3-fold higher level of shear stress on the vessel wall when they are excited with 1.5 MHz compared to 0.5 MHz. And then to test this hypothesis, we performed the experiment using monodispersed affinity bubble, and we found similar level of vessel permeability using these two different frequencies. But interestingly, we found that there is an upregulation of ICAM expression, which is a molecular probe that is sensitive to shear stress in the sonicated region of 1.5 MHz. This data that suggests that we can use the resonance effect to independently tune the different forces exerted by the microbubble oscillation inside the brain. And since ICAM is also an inflammatory marker, it opens up the opportunity not only for controlling the safety of the blood-brain barrier opening, but also great opportunity for promoting immune responses for immunotherapy for brain cancers. So to conclude, larger microbubble with a more elastic shell have stronger oscillation and leads to significantly higher vessel permeability under the same acoustic pressure. The affinity bubble that are excited at 1.5 megahertz result in a similar level of vessel permeability, but a higher upregulation of ICAM expression compared to 0.5 megahertz under the same acoustic pressure. Together, our data shows that microbubble property and their resonance effect can be used to tune the resulting bioeffect, and this finding have a major implication for modulating blood-brain barrier permeability and inflammatory responses. Finally, I'd like to thank all of our lab members and our funding sources. Thank you.